41 million years ago, a 66-foot-long predator with serrated teeth and a sinuous body dominated the world's oceans. This formidable creature was Basilosaurus, a whale unlike any we know today. Its massive size and powerful jaws made it a fearsome hunter, capable of taking down prey as large as other whales. However, Basilosaurus harbored a surprising characteristic that set it apart from other apex predators of its time. Despite its impressive physical adaptations, this ancient whale possessed a brain that was disproportionately small for its body size. This puzzling feature raises intriguing questions about the evolution of intelligence in marine predators and the path that led to modern cetaceans. What factors influenced the development of Basilosaurus, and how does its existence challenge our understanding of predator evolution in the oceans? In 1834, a remarkable discovery in Louisiana sent ripples through the scientific community. Workers unearthed massive, fossilized vertebrae and ribs unlike anything seen before. These ancient remains, initially thought to belong to a colossal reptile, sparked a debate that would reshape our understanding of whale evolution. Dr. Richard Harlan, a prominent American naturalist, first examined the fossils. Struck by their reptilian appearance, he classified the creature as a marine reptile, naming it Basilosaurus, meaning king lizard. This classification seemed logical given the creature's elongated serpentine body structure and the prevailing belief that such large marine predators must be reptilian. As more fossils emerged, conflicting evidence began to challenge Harlan's initial assumptions. The creature's teeth, in particular, held the key to its true identity. Unlike the simple conical teeth of reptiles, Basilosaurus possessed varied dentition, a characteristic of mammals. Richard Owen, a British paleontologist, played a crucial role in correctly identifying Basilosaurus. Owen's expertise in comparative anatomy allowed him to recognize the true nature of the creature. In 1839, he declared that Basilosaurus was, in fact, an early whale, not a reptile. The name Basilosaurus, despite being a misnomer, has persisted. It highlights the difficulties scientists face in interpreting ancient life and reflects the constantly shifting nature of scientific knowledge. The reclassification of Basilosaurus provided concrete evidence that whales had evolved from land-dwelling mammals, a concept still controversial in the mid-19th century. This ancient whale bridged the gap between terrestrial ancestors and fully aquatic whales, offering insights into the dramatic transformations that occurred as these creatures adapted to marine life. As we explore the anatomy of Basilosaurus further, we'll uncover surprising adaptations that made this ancient whale a formidable predator of the Eocene seas, challenging our preconceptions about early cetaceans. Basilosaurus was an ancient whale that challenged our understanding of cetacean evolution, with its unique set of anatomical characteristics. Its most notable characteristic was its long, snake-like body, a sharp contrast to the rounded and streamlined forms seen in modern whales. This slender form, characterized by a long vertebral column and reduced ribcage, likely allowed Basilosaurus to move through the water with a sinuous, eel-like motion. Unlike the powerful tail-driven propulsion of modern whales, Basilosaurus may have relied on undulations of its entire body to swim, a method more reminiscent of sea snakes. One of the most significant anatomical features of Basilosaurus was its heterodont dentition. Its jaw was armed with sharp conical teeth at the front for grasping prey, while the back of its mouth housed blade-like molars for processing its catch. This diverse array of teeth allowed Basilosaurus to effectively capture and consume a wide range of prey. Unlike its modern descendants, Basilosaurus retained elbow joints in its forelimbs. This primitive feature is a clear indication of its transition from land-dwelling ancestors to a fully aquatic lifestyle. The presence of these joints suggests that Basilosaurus may have retained some ability to maneuver in shallow waters, or perhaps even haul itself onto shore for short periods, although its primary habitat was undoubtedly the open ocean. Recent technological advancements have allowed scientists to gain even more detailed insights into Basilosaurus anatomy. CT scans and 3D reconstructions of Basilosaurus isis, one of the species within the genus, have revealed intricate details of its skeletal structure and internal anatomy. These studies have provided new evidence of its aquatic adaptations and have helped to refine our understanding of early whale evolution. Basilosaurus was truly a giant of its time, reaching lengths of up to 18 meters, 60 feet. Its body shape was far more stretched and sleek, giving it a distinctly different profile in the water. This combination of size and shape would have made Basilosaurus a formidable presence in the Eocene seas. The unique anatomical features of Basilosaurus paint a picture of a creature perfectly adapted to its role as an apex predator. These adaptations allowed it to hunt efficiently, process a variety of prey, and navigate its marine environment with deadly precision. As we continue to uncover more about this ancient whale, we gain a deeper appreciation for the diverse evolutionary pathways that led to the cetaceans we know today. In the next section, we'll explore how these anatomical marvels translated into hunting capabilities that made Basilosaurus one of the most fearsome predators of its time. The combination of its unique body plan and specialized features created a hunter unlike anything in the modern ocean, setting the stage for millions of years of cetacean dominance in marine ecosystems. Basilosaurus possessed a secret weapon more devastating than anything found in modern oceans: its incredible bite force. In the world of predators, bite force is a crucial factor in hunting success, determining an animal's ability to catch, kill, and process prey efficiently. For Basilosaurus, this ability was taken to extreme levels. Paleontologists estimate that Basilosaurus could exert a bite force of up to 3,600 pounds per square inch at the tip of its snout. This astounding force surpasses that of modern marine predators and even rivals some of the most formidable extinct species. For instance, it's more than twice as powerful as the bite of a modern saltwater crocodile and approaches the estimated bite force of the massive megalodon shark. The secret to Basilosaurus's incredible bite force lay in its formidable jaw structure. Fossil evidence reveals extreme wear patterns on these teeth, indicating that Basilosaurus likely chewed its food rather than just tearing it apart. This suggests a more complex feeding behavior compared to many modern toothed whales, which typically swallow prey whole. Paleontologists use a variety of methods to calculate the bite force of extinct animals like Basilosaurus. They analyze the structure and attachment points of jaw muscles, the shape and size of the skull, and the wear patterns on fossilized teeth. By comparing these features to those of modern animals with known bite forces, scientists can make educated estimates about the capabilities of prehistoric creatures. The fearsome adaptations of Basilosaurus extended beyond its powerful bite. Its body allowed for quick, graceful movements through the water, perfect for ambush attacks. Its eyes were positioned high on its skull, allowing it to scan the water's surface while remaining mostly submerged. This blend of stealth, strength, and unique hunting adaptations made Basilosaurus a dominant hunter of its era. As we uncover more about Basilosaurus's deadly arsenal, we gain a deeper appreciation for the diverse evolutionary pathways that led to modern cetaceans. This powerful predator reigned over its ecosystem for millions of years, influencing marine evolution in ways we are only now starting to uncover. Unlike the cooperative hunting seen in today's killer whales or the filter feeding of baleen whales, this ancient cetacean was a solitary force in the Eocene oceans. Its hunting behavior more closely resembled that of a colossal aquatic version of a wolf or big cat. Its powerful tail provided bursts of speed for short chases, while sharp serrated teeth were perfectly suited for tearing through flesh and bone. As an apex predator, Basilosaurus had the luxury of selecting from a wide array of prey. Surprisingly, fossil evidence suggests that Basilosaurus had a particular taste for its own relatives. Smaller whales, especially members of the genus Dorudon, seem to have been a favorite meal. This cannibalistic behavior is rare among modern cetaceans and adds another layer of complexity to Basilosaurus's predatory reputation. The ecological impact of Basilosaurus's predatory behavior was profound. As the top predator in its environment, it played a crucial role in shaping the population dynamics of its prey species. The presence of such a formidable hunter likely influenced the evolution of defensive strategies in smaller marine mammals and fish. Moreover, Basilosaurus's position at the apex of the food chain had ripple effects throughout the entire ecosystem. The hunting strategies of Basilosaurus offer a fascinating glimpse into a world where whales were not the gentle giants we know today, but fierce predators that ruled the ancient seas with unparalleled ferocity. This prehistoric super predator's reign shaped marine ecosystems for millions of years, leaving an indelible mark on the course of cetacean evolution. Basilosaurus, despite its fearsome reputation as an apex predator of the Eocene oceans, possessed surprising limitations that challenge our understanding of aquatic predator evolution. These constraints, particularly in diving ability, significantly influenced its ecological niche and hunting strategies. Unlike modern whales, which can dive to depths exceeding 2,000 meters, Basilosaurus was likely confined to much shallower waters. This ancient whale primarily hunted in coastal areas and continental shelves, where prey was more readily accessible. Its restricted diving capabilities had profound implications for its role in marine ecosystems and its vulnerability to environmental changes. Theories on Basilosaurus's swimming capabilities suggest it was an energy-efficient swimmer at moderate depths. However, this same body plan likely limited its ability to make quick, deep dives or engage in prolonged underwater pursuits. Basilosaurus's endurance and swimming abilities remain a topic of scientific debate. Its streamlined body suggests it could cover significant distances, yet its large size and predatory nature likely restricted its range. Modern whales, adapted over millions of years, have specialized circulatory systems and other features enabling them to withstand deep-sea pressures, adaptations Basilosaurus never acquired. These limitations shaped Basilosaurus's role as a coastal predator rather than a widespread marine threat. Restricted to shelf environments, it was likely more vulnerable to environmental shifts, a factor that may have contributed to its eventual extinction. The case of Basilosaurus provides valuable insights into the complex interplay of adaptations and limitations in evolutionary history. Basilosaurus's endurance and swimming capabilities continue to be a topic of scientific debate. While its streamlined, elongated body hints at an ability to cover substantial distances, its large size and active predatory nature likely limited its range. Basilosaurus was well adapted for life in shallow seas, where it could navigate with ease and efficiency. However, it may have faced difficulties in venturing into the deeper waters where modern whales thrive. Unlike modern whales, Basilosaurus lacked the ability to dive deeply. As a representative of an early stage in whale evolution, it retained many traits from its land-dwelling ancestors, limiting its physiological adaptations for life at great depths. In contrast, modern whales have undergone millions of years of specialized evolution, developing unique circulatory systems and other adaptations that allow them to endure the immense pressures of deep-sea environments. This lack of adaptations in Basilosaurus confined it primarily to coastal and shelf areas, making it a specialized predator of these regions rather than a dominant force throughout the oceans. Consequently, its restricted range made it more vulnerable to environmental shifts, possibly contributing to its eventual extinction as conditions changed and its shallow water habitat became less favorable. Interestingly, while Basilosaurus limbs harken back to its terrestrial past, its teeth point towards its specialized marine future. The ongoing study of Basilosaurus and its vestigial limbs continues to provide valuable insights into the evolutionary process. As new fossils are uncovered and cutting-edge analytical techniques are applied, our understanding of whale evolution grows ever more nuanced. From the lush mangroves of ancient Egypt to the vast seagrass meadows of prehistoric oceans, Basilosaurus left its mark across a world we can scarcely imagine. This ancient whale dominated an ecosystem that would be utterly alien to modern marine biologists. Unlike the vast open waters of today's oceans, the Eocene seas were characterized by extensive shallow continental shelves and warm tropical conditions that extended much further towards the poles than they do now. The world Basilosaurus ruled was a paradise of productivity. These underwater prairies supported a diverse array of creatures, from small fish and invertebrates to larger prey that would eventually fall victim to Basilosaurus's powerful jaws. The abundance of these seagrass ecosystems likely played a crucial role in supporting the massive energy requirements of this 60-foot predator. As the top predator, Basilosaurus exerted significant pressure on its ecosystem. Its presence likely drove unique evolutionary adaptations in its prey species. Some paleontologists theorize that Basilosaurus may have played a role in shaping the evolution of other marine mammals, potentially influencing the diversification of early cetaceans in ways distinct from other predators of its time. The reign of Basilosaurus as the dominant predator of the ancient seas lasted for an astonishing 7 million years, from approximately 41 to 33 million years ago. This extended period of dominance is a testament to the effectiveness of Basilosaurus's adaptations and its ability to thrive in the warm, productive oceans of the Eocene. For context, modern humans have only existed for about 300,000 years, making the reign of Basilosaurus more than 23 times longer than our entire species' existence. The factors that led to its downfall were likely complex and multifaceted, involving changes in global climate, shifts in ocean chemistry, and the evolution of new competitors. These changes not only affected Basilosaurus, but also set the stage for the diverse marine ecosystems we see today. As we explore the intriguing story of Basilosaurus, we encounter a puzzling paradox that complicates our understanding of predator evolution. Despite being a massive 60-foot-long marine predator armed with powerful jaws, Basilosaurus had a surprisingly small brain, about the size of a modern dog's. This surprising fact raises questions about the role of intelligence in the success of ancient marine predators and has left scientists contemplating its evolutionary significance. The small brain of Basilosaurus challenges the notion that advanced cognitive abilities are essential for a successful predator. Basilosaurus likely thrived without sophisticated hunting strategies or social coordination. Its modest brain size suggests a solitary, instinct-driven lifestyle, relying more on physical adaptations, such as its elongated serpentine body, than on learned behavior or teamwork in hunting. Several theories attempt to explain why Basilosaurus evolved with a small brain relative to its size. One hypothesis is that maintaining a large brain would have been energetically costly for an active predator in the warm, prey-rich seas of the Eocene era. Another theory posits that Basilosaurus's hunting approach didn't demand advanced cognition. Its body structure and jaws were already well-suited to capturing prey, making complex problem-solving unnecessary for its survival. Basilosaurus's smaller brain had significant implications for its behavior. With limited capacity for problem-solving or social interactions, this ancient whale likely used straightforward hunting methods. Its success in such a relatively simple behavioral niche demonstrates that, in specific ecological conditions, physical prowess and basic instincts can be as advantageous as cognitive complexity. This paradox suggests that large brains and complex social behaviors, typical of modern cetaceans, are relatively recent developments in their evolutionary history. The case of Basilosaurus exemplifies the diverse paths that evolution can follow, showing that intelligence isn't always the favored trait in predator development. This ancient whale's success, despite its small brain, opens up new research avenues in understanding cognitive evolution in marine mammals. For millions of years, Basilosaurus reigned as the apex predator of the Eocene seas. Its powerful jaws and elongated body-shaped marine ecosystems across the globe. Yet, like many great predators, Basilosaurus eventually met its demise. The extinction of this ancient whale superpredator remains one of paleontology's most intriguing mysteries, challenging our understanding of Earth's prehistoric past. While species extinction is a natural part of Earth's evolutionary history, the cause of Basilosaurus's disappearance is not immediately clear. Several competing theories have emerged to explain the downfall of this once dominant predator, each offering a unique perspective on the changing world of the late Eocene. One theory suggests that Basilosaurus struggled to adapt to the loss of its preferred hunting grounds. As global temperatures cooled and sea levels dropped, the warm, shallow seas that had been Basilosaurus's domain began to recede. This habitat loss may have severely impacted the ancient whale's ability to find suitable prey, leading to a gradual decline in population. Another factor that likely contributed to Basilosaurus's extinction was the emergence of new competitors. The late Eocene and early Oligocene saw the evolution of more derived cetacean species better adapted to the changing marine environment. These more recent whale species, characterized by their sleek bodies and sophisticated social behaviors, may have outcompeted Basilosaurus for resources and eventually replaced it as the dominant marine predators. Fossil evidence provides some clues to the final days of Basilosaurus. The fossil record shows a significant reduction in Basilosaurus populations leading up to its extinction, suggesting that the species was already struggling to adapt to changing conditions. This gradual decline, rather than a sudden disappearance, points to a complex interplay of factors that ultimately led to the species' extinction. Some researchers propose that Basilosaurus's specialized adaptations, once the key to its success, became liabilities in a rapidly changing world. Its large size and high energy requirements may have made it particularly vulnerable to shifts in prey availability and distribution. Additionally, its solitary nature and potentially low reproductive rate could have hindered its ability to recover from population declines. The extinction of Basilosaurus may have also been influenced by changes in ocean chemistry and productivity. Alterations in ocean circulation patterns and nutrient availability could have disrupted the marine food webs upon which Basilosaurus depended. If its preferred prey species were affected by these changes, Basilosaurus may have struggled to find adequate nutrition to sustain its large body size. Ultimately, the extinction of Basilosaurus was likely the result of a perfect storm of environmental and ecological factors. Its inability to adapt quickly enough to the changing conditions of the late Eocene and early Oligocene sealed its fate. As we continue to unravel the mysteries of Earth's prehistoric past, the legacy of Basilosaurus lives on, shaping our understanding of whale evolution and the complex dynamics of ancient marine ecosystems. While Basilosaurus vanished from Earth's oceans millions of years ago, its impact on scientific understanding continues to grow. This ancient whale, once misidentified as a marine reptile, remains a crucial subject in paleontology and evolution studies. Recent research has shed new light on Basilosaurus, enhancing our knowledge of prehistoric marine ecosystems. Ongoing studies have focused on Basilosaurus's feeding habits, social behavior, and geographic distribution. Advanced imaging techniques and 3D modeling now allow scientists to reconstruct its musculature and biomechanics with unprecedented accuracy. In 2019, a remarkable discovery in Wadi al-Hitan, Egypt, known as the Valley of the Whales, revealed a Basilosaurus fossil with the remains of other marine animals preserved in its stomach contents. This finding provided direct evidence of the creature's diet and its position as a predator. Such discoveries continue to refine our understanding of ancient food webs and the ecological roles played by prehistoric marine mammals. The study of Basilosaurus has also contributed to our understanding of how evolutionary adaptations occur. Its unique features offer valuable insights into the changes that took place as early whales transitioned to life in the oceans. For example, the structure of Basilosaurus's inner ear bones provides crucial information about the development of underwater hearing abilities in cetaceans. Recent studies have explored topics such as the creature's thermoregulation, diving capabilities, and potential migratory patterns. These investigations not only enhance our understanding of Basilosaurus itself, but also provide a broader context for studying the evolution of marine mammals and the dynamics of ancient ocean ecosystems. The legacy of Basilosaurus extends beyond its direct contributions to whale evolution studies. The journey from its initial misidentification to its correct classification highlights the importance of continual reassessment and analysis in scientific research. As we reflect on the significance of Basilosaurus, we are reminded of the dynamic nature of life on Earth. This ancient whale, once the ruler of Eocene seas, now exists only as fossilized remains. Yet, its story continues to evolve as new discoveries shed light on its life and times. The tale of Basilosaurus serves as a reminder that in the grand tapestry of evolution, even the mightiest creatures are temporary players, their reign inevitably giving way to new forms of life, adapted to an ever-changing world. Basilosaurus serves as a striking reminder of Earth's ever-evolving life, where even dominant species face the relentless forces of environmental change and competition. Though this ancient whale thrived in the Eocene's warm, shallow seas, its era eventually ended, underscoring the fleeting nature of ecological dominance. The world it inhabited, rich in prey and unique conditions, may be gone, but its legacy lives on in the diverse cetaceans that populate today's oceans. The story of Basilosaurus exemplifies evolution's continuous role in shaping life. This ancient predator adapted to its environment, yet faced new challenges as conditions shifted over millions of years. Studying Basilosaurus provides insights into the intricate relationships between species, ecosystems, and environmental pressures. As we confront modern ecological issues, the lessons from Basilosaurus remind us of the delicate balance needed to sustain life and the importance of preserving our ocean's biodiversity for the resilience of our planet's future.